Hello, friends. In lecture 3 of this combinatorial mathematics, we shall discuss about the partition of a set. So, you see, first we'll see the definition of partition of a set, then some examples, and how this helps in the enumeration or in the combinatorial studies. Something will be discussed regarding that. So, the definition of partition is that let x be a set, and x1, x2, xn be non-empty subsets of this. The subset form the partition p of x if the union of subsets in p is equal to the x itself. That is, x equal to x1 union x2 union and so on up to union xn. One more thing, that a partition never contains the empty set, and the intersection of any distinct subsets in P is empty. In fact, we can say that xi intersection xj will be equal to phi whenever I not equal to j. So here we are saying that the intersection of two distinct sets is empty. So then it forms a partition. So let us see in one example regarding this. And I ask you, which of the following collection of subsets of this A forms a partition? So this is one collection A. Is it a partition? This is the second collection. This is the third collection. And now we are having the fourth collection. So which one among these is a partition of set A? So you can clearly see that you can consider this is x1, this is x2, x3, and x4. And if you take the union of these, we can get this A. And one more thing, if you take the intersection of any of these two, so definitely that will be empty. And there is no empty set among these, so therefore it forms a partition. Now, if you look at the second part, you can see the intersection of these two. Here are only two subsets, x1 and x2. You take the intersection, so definitely that is not phi because their intersection is b. So this is not a partition. It contains the empty set, so not a partition. And here, intersection is phi, and this the union of these two is giving this set A itself. So this is also a partition. So this is an example regarding the partition. Now again, come back to the same example but in a different way. Let A is the set here, and how many partitions we can obtain. So as discussed in the last slide, we can obtain five partitions here: P1, P2, P3, P4, and P5. Okay, and there will be no other partition other than these. So in this way, we can say that we can have five partitions for a set of three elements. Now if we have four elements in a set, then how many partitions will be there, right? So this is the question that lead us to some kind of enumeration type of study, so that becomes part of the combinatorial studies. So for finding the exact number of partitions in a set, exact number of how we can determine the exact number of partitions of a finite set, this led us to some concept, that is the equivalence, as we have discussed in the last class, equivalence relations. So this concept of equivalence relation on a set is related to the computation of exact number of partitions of a finite set. So we'll see it in the next lecture. Thank you.